Hello everyone, my name is Rizwan Tariq Sayed and I am a research scientist in IHP Microelectronics. The topic of my presentation is Fault Resilience Analysis of Quantized Deep Neural Networks. Whether we observe it or not, AI has been an integral part of our lives. It has really impacted a lot of areas in the field of science and technology. From Netflix movie recommendation to online ID verification, everything sort of revolves around the use of AI algorithms. Deep learning is one of the most hot topics in research for many years now. And because of its state of the art results in prediction, classification, and natural language processing, it's now being used in safety critical applications as well. And in our group in IHP, we are exploring the use of AI in safety critical application, or in other words, fault tolerant AI processing systems. And when we talk about safety critical applications, there are generally two applications which comes in our mind, and one of them is autonomous vehicles and the other is space. As we know that autonomous control requires intelligence, and deep neural networks has shown it time and again that they can assist us in taking intelligent decisions. And as we are familiar that the automotive industry has been actively using deep learning to push their vehicles to level 5 autonomy for use cases such as object detection, path planning, and depth estimation. We have been actively using deep learning in automotive industry. For space industry as well, autonomy is very important as the communication channel between the spacecraft and the Earth is very limited. For example, recently Mars rover, which was named Perseverance, landed on Mars autonomously. There is an 11-minute communication delay between the Earth and the Mars, so a real-time control of the Mars rover is not possible. And as we have also seen that space missions are increasingly become frequent and complex. So there is a growing demand for autonomous control in the space industry. Neural networks are eventually going to be implemented on hardware. And the hardware consists of computational elements and storage elements such as flip-flops, memories, and DSP blocks. But we also know that hardware is prone to errors. Therefore, we have to make our hardware safe enough so that we can run AI algorithms for safety critical applications. And why our hardware is vulnerable and why our hardware is prone to errors, it is because high energy particles and radiation strikes. The high energy particles can affect our hardwares and can induce hard errors or soft errors. These hard and soft errors compromise the system functionality by causing permanent damage or bit flips in the memory or computational elements. Imagine a self-driving car scenario. In a fault-free execution, the car will be detecting this as a truck and brakes will be applied. In case there is a fault occurs in the system or in the neural network and there has been a misclassification, so the truck could be classified as a bird and the brakes may not be applied by the car. So whether in space or on Earth, radiation strikes are able to affect the behavior of our modern processing systems, and this can eventually lead to failure or data corruptions. And that's why our hardware should be thoroughly verified and it should be fault tolerant or it should be radiation hardened so that we can use this hardware in safety critical applications. Now we will briefly discuss what are the different factors that affect the resiliency of the neural networks. So when a fault is injected in the network, it can affect the output of the neural network, and how much it is going to impact the output, it depends on a lot of different factors. For example, network architecture. There are so many different network architecture. Some are similar to each other, but some are very different from each other. So the impact of a fault depends on the network architecture as well, whether we are using batch normalization layers or how deep the network is or how many branches does the neural network has. For example, if you use the batch norm layers, it generally reduces the impact of the faults. And we have also seen that if the deeper the network is, the more resilient it's going to be. And it also depends on the layer type. What are the different layer types? For example, if the fault is injected in the fully connected layer or it is injected in the convolutional layers. For example, convolutional layers, when a fault is injected in the convolutional layers are less resilient, and you will most likely to see a large decrease in the accuracy if you have a fault in the CNN layers. Model compression. For edge devices, particularly, model compression is really necessary. The goal of the model compression is basically to achieve a model that consumes less computational resources without significantly decrease in the accuracy. And there are two important model compression techniques. For example, one is pruning and the other is quantization. And in pruning, we are basically removing unnecessary connection, and in quantization, we are reducing the precision of our network's weights. And the model compression also affect the resiliency of the network. What data type are we using to represent the neural network weights is going to also play an important role. For example, if you are using floating point 32, floating point 16, or fixed point values, these things really matter. When a fault is injected, it can really impact the output of the neural network. Bit position has also a role to play. For example, if a fault is injected in the higher order bits, it will cause a large deviation in the magnitude, and hence it will also impact the accuracy of the network more. So data reuse buffers. So data reuse buffer is not really a property of the DNN itself, but it's more like how you have implemented networks on the hardware. For example, if a fault occurs in a data buffer which is being reused, this can be a problem because the faulty value will be getting reused again and again. And as I said, in this presentation, we are going to be focusing on the quantization aspect of neural network and how quantization affect the resiliency of the neural networks. Now let's talk about quantized deep neural networks. So we are generally aware that we have limited memory and computational resources in the hardware. And what quantization does, quantization reduces the precision of the number, and it sort of converts the 32-bit floating point representation to low bit width fixed point value. And this leads to having a smaller model size and faster computation. And when we have a smaller model size and when we are taking less hardware resources, this can also mean that we have reduced power consumption as compared to floating point 32 processing. And this can also reduce the latency because now we have simplified the calculations, because in floating point 32 numbers, you need extra additional hardware. That additional hardware can add latency to your design. So we can also skip additional floating point units, and as I said, this can also help us reduce the latency and also the power, and ultimately it will cost less hardware resources. And if you have a look on the right, you can see that this graph is a bit more continuous than this graph. This graph, which is on floating point 32, it has more dynamic range. And this graph, which is just using 4-bit fixed point, it has very less dynamic range. You can say that a lot of the gaps in the weights, because these values in these gaps cannot be represented by 4 bits. And we will also see later in the slide that even just 4 bits, we can maintain the desired accuracy. But let's also talk about the impact of a fault when we use floating point numbers and when we use fixed point numbers. Imagine 0.25 is one of the weight of the neural networks. And if this weight is represented as floating point 32, you can see that 0.25 can be represented by this value. And if we represent 0.25 by a fixed point 4-bit value, it can be represented like this. So if a fault occurs on the MSB of the floating point number, which is the weight of our neural network, it can change the weight value to this huge number, and this can totally saturate our network. While if the fault occurs on the MSB of the fixed point number, it will only change its value from 0.25 to 0.75. It will also cause decrease in the accuracy, but not as much as the floating point numbers. So when we talk about quantization in neural networks, There are generally two methods with which you can do quantization. One is post-training quantization and the other is quantization-aware training. In post-training quantization, you first train your model in floating point 32-bit, and once the model is trained, you can later convert the model to lower precision models. This step is generally simpler to do and very straightforward, but the problem is that it can lead to some accuracy degradation. The method that we have followed in this paper is quantization aware training. In this method, we train the model directly in the lower precision. This takes more time, but it can help us attain better accuracy. So in general, with the help of quantization aware training, we can achieve better accuracy as compared to post-training quantization. And further in the quantization, there is homogeneous quantization and heterogeneous quantization. In homogeneous quantization, all the layers of the neural network are quantized to the same bit width. So basically it's easy to use and you can just use the same bit width for all the neural network layers. So in our case, model 1 to 7 are homogeneously quantized, which you can see in this table. While in heterogeneous quantization, we can selectively choose quantization bit widths for different layers in a neural network. This can drastically increase more design parameters. In our study, model 8 to 12 are heterogeneously quantized. So you can see that the model 7, which is 32-bit homogeneously quantized, has 95.65 accuracy, and as you are decreasing the bit width, the accuracy is kind of maintained at 95%. But if you quantize it more, you can see that the accuracy start to also decrease a little bit. And the model 12, which is the most quantized model in our study, you can see that it has the least accuracy also because we have quantized it more aggressively. And this is the network architecture. We have a 3-layer neural network architecture, and the details of the architecture you can see in the table. Let's also discuss how this fixed point data type is arranged. So this is the number of integer bits and this is the number of fraction bits, which includes also a sign bit. This is the case of a fixed point format of 3-bit QDNN. Now let's talk about the fault model that we have used in our paper. We have considered soft errors modeled as bit flips in the weights of the quantized deep neural network. They're also called single event upsets. We have only injected faults in the weights of the QDNN model, and we have ignored the fault injection in biases because 99% of the parameters in the model are weights, and as per different studies, fault injection in the biases of the DNN doesn't affect the DNN accuracy. This is a compressed version of the table, and you have already seen a detailed table in the previous slide. We have injected faults in 12 different models. Model 1 to model 7 are homogeneously quantized, and model 8 to model 12 are heterogeneously quantized. The data set that we have used in MNIST and a bit error rate from 0 to maximum of 10%. And this platform and libraries are pretty standard. To simulate quantization neural networks, we have used QKeras 0.8 version. In our final section, let's discuss the fault analysis results. This is the layer 1 fault analysis of the neural network. The general trend shows that with the increase in the model compression, there is an increase in the resiliency of the DNN model. For example, if you see on the left graph, these are model 1 to 7, these are homogeneously quantized layer 1, and this graph is the layer 1 fault analysis of the model 8 to 12, which are heterogeneously quantized. The accuracies and the levels of quantization you can see in the table, and this is the neural network architecture we have also discussed before. Model 7 has the highest starting frequency you can see here, and this is 32-bit quantized, and model 12 has the least starting frequency, which is this one, and this is the most aggressively quantized. But if you compare model 7, which is 32-bit quantized, with model 1, which is 3-bit quantized, we get an accuracy benefit of just 2.54% and 0.65% benefit as compared to model 2. The general trend shows that the resiliency of the DNN model increases with the increase in the model quantization. As you are quantizing the models more and more, the resiliency is increasing, and in layer 1 of model 1, which is 3-bit quantized, is more resilient as compared to Model 7 Layer 1. And if we talk about Layer 1 fault analysis of heterogeneously quantized models, we will see that more or less these models have the same resiliency pattern because they are quantized to somehow similar number of bits. We also have to take into account that with more aggressive quantization, this can lead to decrease in accuracy and also decrease in resiliency as compared to its other counterparts. So overall, Model 8 and 10 have 20.7% better resiliency in layer 1 as compared to Model 7, which is 32-bit quantized. This is the layer 2 and layer 3 analysis. The general trend is layer 2 and layer 3 are more resilient to faults as compared to the layer 1, but their resiliency seems to decrease with the increase in compression. This is the layer 2 fault analysis of all the models, and this is the layer 3 fault analysis of all the models. Two important points here. So layer 2 and layer 3 are more resilient to faults as compared to layer 1. And the reason why layer 2 and layer 3 are more resilient as compared to layer 1 is that layer 1 consists of 25,120 parameters if you look at the QDNN architecture, which is 18.12 times the parameter of layer 2 and layer 3. This means that layer 1 takes more computing resources and the probability of faults in layer 1 is higher. And the second point is the resiliency is decreasing in layer 2 and layer 3 as we are increasing the model quantization. For example, if you have a look at this green graph, which is model 7, it seems to be more resilient in layer 2 and layer 3, while as we are increasing the model quantization, the layer 2 resiliency is decreasing. So finalizing a model could depend on a lot of factors: available computing resources, desired reliability, latency, and accuracy. Therefore, based on the analysis that we have done, Model 8 and 9 seems to have better accuracy with less computing resources. And both models also surpass others in terms of resiliency. So in this presentation, we analyze the resiliency of 12 quantized models, which includes homogeneous and heterogeneous quantized models. Fault injection experiments are performed to introduce errors in the weights of the DNN model. And the fault model was single event upsets in the weights memory. We have concluded that resiliency of the DNN model increases with the increase in model quantization, but when you do more aggressive quantization, that could also compromise the accuracy and resiliency, because with more aggressive quantization, your significant bits are exposed to faults, which can cause to decrease in the resiliency. And as we have also discussed, Model 8 and 9 are generally a good choice because they are better in terms of resiliency and utilization of hardware resources. This presentation was limited to fault analysis of quantized deep neural networks, but in future, we would like to explore some hardware-only or hardware-software co-design methods which can make our deep neural network fault tolerant. Thank you so much for your time. If you have any questions, feel free to write me.